जी बेटा, अस्सलाम वालेकुम. All right, so basically this is Feb-March 2022, paper 22. Right, so this is the most recent paper and was much awaited paper as well before May-June series, because this is the first paper based on the new syllabus. So as soon as I get my hands over this paper, I started solving it, and today I'm posting it with you guys, right? So let's start with the question number 1. Now, in the first question, this is related to periodicity, period 2. Figure 1.1 shows how first ionization energy varies across period 2. So they've given us a trend of ionization energies across period 2, right? Construct an equation to represent the first ionization energy of oxygen, include state symbols as well. So first ionization energy is the energy required to remove 1 mole of electron from 1 mole of gaseous atom to form 1 mole of gaseous ion. So we have to write the ionization energy for oxygen. So that would be 1 mole of oxygen in gaseous state loses 1 mole of electron to become O plus in gaseous state. So 1 mole of electron from 1 mole of gaseous atom to form 1 mole of gaseous ion. So this is the first ionization energy. Now the next question is, state and explain the general trend in first ionization energy across period 2. Right, so across the period, ionization energy increases. As we move from left to right in periodic table, the ionization energy increases, right? And the reason is, so let's just write the trend. The ionization energy increases across the period due to increase in nuclear charge or number of protons, right? As we move from lithium to neon, lithium has 3 protons, or its atomic number is 3, then beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. So the number of protons are increasing, and as number of protons increases, because number of shells are same, they all belong to second period, so that means they all have 2 shells, right? So the number of shells and obviously the shielding effect, if number of shells are same, that means shielding effect would also be same. Shielding effect are similar, so it becomes difficult to lose electron because number of shells are same, shielding effect is same, but nuclear charge, number of protons are increasing, right? So they would attract the valence electron more, so it would become difficult to lose electron. So as nuclear charge is increasing, number of shells are same, shielding effect are same, it becomes difficult to lose electron. All right. Now the next question is, explain why the ionization energy A in figure 1.1 does not follow the general trend in the ionization energy across period 2. So A is not following the general trend, right? There is another element which is not following the general trend, but here they're only talking about A. So A is oxygen, and oxygen is after nitrogen. The trend is of increasing ionization energy, but as we can see that the ionization energy of oxygen is less than that of nitrogen, although its atomic number is higher as compared to nitrogen, but still it is easier to remove electron from oxygen. So what is the reason behind it? The reason behind it is the electron configuration of oxygen and nitrogen. So if we write the electron configuration of nitrogen, nitrogen has its atomic number is 7. So its configuration would be 1s2, 2s2, 2p3, and in 2p, in p subshell, it has 3 degenerated orbitals, and degenerated orbitals are those which have same energy but they're differently oriented in space. So 2px, py, pz. So these 3 electrons, nitrogen has 3 electrons in each of its degenerated orbital. So they are filled according to Hund's rule, that the degenerated orbitals would be filled singly first and then doubling takes place. So this is the electron configuration of nitrogen orbital wise. And if we write for oxygen, oxygen has 8 electrons. So that means 1s2, 2s2 and 2p4. So in case of nitrogen, there are 4 electrons in p subshell. So that means px, py and pz. So 1 electron in px, 1 in py, 1 in pz, and then doubling takes place in px, because once all the degenerated orbitals are singly filled, then doubling takes place. So that means in case of nitrogen, the electron is being removed from the unpaired orbital, unpaired degenerated orbital. This is unpaired degenerated orbital, right? But in case of oxygen, it is being removed from the paired degenerated orbital. Paired degenerated orbital. So in paired orbital, there would be repulsion, right, between electrons due to same charge. So these electrons, they are repelling each other. These electrons present in the degenerated orbital in px, they are repelling each other, and due to this repulsion, although the nuclear charge or the number of protons of oxygen is higher as compared to nitrogen, but this repulsion will offset the nuclear charge, and this would become the primary factor. And that is why the ionization energy of oxygen, or the energy required to remove electron from oxygen, is less as compared to the energy required to remove electron from nitrogen. So we can say that the valence electron of oxygen is in paired degenerated orbital, which is easier to remove due to electronic repulsion. All right, so this would be the answer for the question. Now the last part of this question is element E in period 3. Now they're talking about period 3. So element E is in period 3 of the periodic table, right? Element E. The first 8 ionization energy values of E are shown in table 1.1. Right, so the first 8 ionization energies value of E are shown in table 1.1. So these are 8 ionization energies. Now what we have to do, deduce the full electron configuration of E. Explain your answer, right? So now for the full electron configuration, we have to find out which element is E. And as they have given us the 8 ionization energies, now we have to find out how many valence electrons it has, like to which group it belongs. So if you look at these ionization energies increases. For second is greater than first, then third is greater than second due to increasing effective nuclear charge. But you can see that there is a large difference. There is a huge difference between third and fourth, right? So that means fourth electron is being removed from a lower shell, right? Whenever there is a shell change, whenever we move from a higher to a lower energy level, there would be a huge energy gap, right? So that huge energy gap is between third and fourth. So that means this element E has 3 electrons in its valence shell, and the element in third period, which has 3 electrons in valence shell, that means it belongs to group 3, right? It belongs to group 3. So that would be aluminum. Aluminum is the element of period 3 which belongs to group 3 as well, right? So you can see in the periodic table. And one more thing about this paper, I forgot to mention this thing in the start. Basically now you will not get any data booklet, right? You will get all the details or all the tables or any information you need, you will get this with this paper, right? Like if you read the instructions, the total marks for this paper is 60. The number of marks for each paper question. All right, the periodic table is printed in the question paper. Important values, constants and standards are printed in the question paper. So all those students who are thinking or who are asking again and again, okay, do we have to remember the values in the data booklet? So no, you don't have to remember, or you don't have to memorize the values, because you will get all those things in the paper, right? No data booklet this time, but all the values, all the tables, or the important information will be with your paper. So you don't have to memorize all those things, okay? All right, so we have to find out an element which belongs to period 3, and it is a group 3 element, so that is aluminum, right? This is aluminum. Aluminum belongs to period 3. This is first period, second period, and this is third period. So third period, and this is group 3. So this is aluminum, and aluminum has 13 electrons. So now we have to write the electron configuration for aluminum. So full electronic configuration of aluminum would be 1s2, 2s2, 2p6, 3s2, 3p1. So this would be the electron configuration of aluminum. And explanation, like on what basis we have decided that this is aluminum. So because it has a huge difference in third and fourth ionization energy. Means third electron means 3 electrons, or first 3 electrons are in valence shell, and fourth electron is removed from a lower shell. Fourth electron is removed from a lower shell. All right, so this would be the answer to the question, and this was question number 1. Now the second question is, some oxides of elements in period 3 are shown, right? So here we have some oxides starting from sodium oxide, aluminum oxide, phosphorus oxide. Sodium reacts with oxygen to form sodium oxide. Sodium is the reducing agent in this reaction. So define a reducing agent. So reducing agents are basically, these are those elements or compound in a redox reaction which loses electron, or we can say which get oxidized, or which reduces the other substance. So basically it loses electron, it get oxidized and reduces the other substance. So a reducing agent is a substance which reduces other substance by oxidizing itself, by losing electrons, right? Okay, so the next part is, write an equation for the reaction of sodium oxide with water. Sodium oxide reacting with water. So sodium oxide is a basic oxide and it is water soluble as well. So when we dissolve sodium oxide in water, we get an alkalinic solution, sodium hydroxide. And to balance it, we will write 2 with sodium hydroxide. So this is the equation for the reaction of sodium oxide with water. Now, the next part is Al2O3 aluminum oxide is an amphoteric oxide found in bauxite. State what is meant by amphoteric. So amphoteric, what is meant by amphoteric? A compound which is able to react with both, both as an acid or as a base, both as an acid and base, means which can react with acids and base. Those are known as amphoteric substances. So it is an amphoteric oxide. All right, then they're saying that Al2O3 is purified from bauxite in several steps. The first step involves heating Al2O3 with an excess of NaOH, because Al2O3 is an amphoteric oxide, right? This is an amphoteric oxide, so it can react with base. So a colorless solution forms. a colorless solution forms. Write an equation for this reaction when Al2O3 react with aqueous sodium hydroxide. So we know this thing. This is the equation from your syllabus, that when Al2O3 reacts with sodium hydroxide in aqueous medium, right, in aqueous medium, so we get a hydrated salt which gives a colorless solution. So that would be NaAlOH4, right? And to balance the equation, we will write 2 with this hydrated salt and 2 with the sodium hydroxide. And now we have 8 hydrogens, 2 with sodium hydroxide, so 3 2s are all right. So now this is a balanced equation. So this would be the equation when Al2O3 reacts with an excess of NaOH aqueous. All right, now the next part of the question is Al2O3 is used as a catalyst in the dehydration of alcohols. Right, in the dehydration of alcohols, when water is removed from alcohols and we get alkenes. State the effect of using Al2O3 as a catalyst in the dehydration of alcohols. Use the Boltzmann distribution in figure 2.1 to help explain your answer. So they have given us this Boltzmann distribution graph, and we have to explain the effect of using Al2O3 as a catalyst in the dehydration. So what effect Al2O3 has on the dehydration of alcohol? So we know this thing, that catalyst increases the rate of reaction and by lowering the activation energy. So on the graph, we would just simply show that, let's suppose this is the activation energy for the uncatalyzed reaction. So before we were using Al2O3, only these particles were involved in the reaction. Let's say these particles were involved in the reaction. But in the presence of the catalyst, what happens is activation energy gets lowered down. The energy barrier gets lowered down. So let's suppose this is the activation energy. This is the activation energy for catalyzed reaction. So that means now a higher fraction of particles are involved in the reaction. So now these particles can also take part in the reaction. So what is the effect of catalyst on the dehydration of alcohol? It increases the rate of dehydration, right? It increases the rate of reaction by lowering the activation energy so that more particles can take part in the reaction. More collisions takes place, more frequent effective collisions or more effective collisions. Right, so it converts the ineffective collisions into effective collisions by lowering the activation energy. So P4O6 is a white solid. P4O6 is a white solid that has a melting point of 24 degrees centigrade. Solid P4O6 reacts with water to form H3PO3. Deduce the type of structure and bonding shown by P4O6. Explain your answer. So the type of structure and bonding, they're telling us that it has a melting point of 24 degrees centigrade. That means a low melting point. That means it is a simple molecular structure. And type of bonding would be covalent bonds. So the answer would be, it is a simple molecular structure. Simple molecular structure. And in P4O6, the phosphorus and oxygen are bonded to each other through covalent bonds. Phosphorus, the molecular structure we are talking about, the phosphorus and oxygen, they are bonded to each other. Through covalent bonds. right? So now the next part is determine the oxidation number of phosphorus in H3PO3. So in H3PO3, we know this thing that oxygen is an oxidation state, sorry, H3PO3. So in H3PO3, oxygen is an oxidation state of -2, it becomes -6. So this must be overall +6, so to make it +6, hydrogen with non-metals is an oxidation state of +1. So this becomes +3, that means phosphorus is +3 as well. So +3 becomes +6. So the oxidation number of phosphorus in H3PO3 is +3. All right, now the next question is related to energetics, and they're saying it that when P4O6 is heated with oxygen, it forms P4O10 solid. It gets further oxidized. And here is the equation for the reaction of P4O6 with oxygen. Delta HR is given. This is -1372 kilojoules per mole. The enthalpy change of formation of P4O10 is 3012 kilojoules per mole. So now the best technique to solve these type of questions is that write down all the equations they have given you or draw a cycle, right? So the first equation, which is already mentioned in the question, is the P4O6 getting oxidized. It forms P4O10 solid. Its delta H is already given. And then they have given us the enthalpy change of formation. And what is formation? When 1 mole of a substance formed from its elements under standard condition. So the formation of P4O10, this P4O10, its formation is given. So it would be formed from its elements under standard conditions. So we would have P4 or 4P, whatever you can write. So P4 or 4P plus reacting with 10 oxygen. So the standard state of oxygen is diatomic form, right? So these two elements, they will combine to form P4O10, and the delta H formation for this reaction is -3012, right? This is the best technique to solve these questions, right? All the reactions, make a cycle of your own and decide then what you have to find out. So the delta HR, this reaction was already given. We have written the formation of P4O10. Now what we have to find out is calculate the enthalpy change of formation of P4O6. We have to find out the formation of P4O6, right? So the elements are already mentioned here. So we just have to draw an arrow. This would be the formation of P4O6, and this we have to find out. Right, this formation we have to find out. So this is the cycle. Now we already know two of the energy values. This one is -1372. This is -3012. And if you look closely, this arrowhead is combining with this arrow tail. So we will add these two together. Right, these two together. According to Hess's law, the energy change during a chemical reaction does not depend upon the path taken. It would be same. So either we convert phosphorus or oxygen directly into P4O10, or we first convert it into P4O6 and then into P4O10. The energy change would be same. Now let's write the equation. So delta H formation of P4O10, this energy change would be equal to delta H formation of P4O6 plus delta HR. Okay, so the formation of P4O10 is -3012, which is equal to formation of P4O6. This we have to find out, and the delta HR is -1372. Okay, so X would be equal to -3012 plus 1372. And if we solve this thing, so -3012 plus 1372. So that is equals to -1640. All right, this is equal to -1640. 1640. All right, now the next question is, write an equation for the reaction of P4O6, P4O10 reacting with water. Now P4O10 is an acidic oxide, so when it dissolves in water, it will lower down the pH. So P4O10, when reacts with water, we get phosphoric acid H3PO4. And to balance it, we would write 4 with H3PO4, and now we have 4 3 are 12 hydrogens, so 6 2s are 12, and oxygens are now balanced. So the next part of the question is related to sulfur and nitrogen. Sulfur dioxide and sulfur trioxide are found in the atmosphere. The oxidation of SO2 to SO3 in the atmosphere is catalyzed by NO2. The oxidation of SO2 to SO3 is catalyzed in the atmosphere by NO2. The first step of the catalytic oxidation is shown in equation 1. So this is equation 1 where SO2 is reacting with NO2 and it converts into SO3. So that means NO2 is acting as an oxidizing agent as well, and we get NO, nitrogen monoxide. Now construct an equation to show how NO2 is regenerated in the catalytic oxidation of SO2, because NO2 is acting as a catalyst, so it must be regenerated. And how it regenerates in the air, it reacts with nitrogen monoxide, it reacts with oxygen, get oxidized and convert back into nitrogen dioxide. And to balance it, we write 1/2 with the oxygen. All right, so this is the balanced equation. Now the next part is NO2 can also react with unburned hydrocarbons to form photochemical smoke. State the product of this reaction that contributes to photochemical smoke. The products of the reaction when NO2 reacts with unburned hydrocarbons. So basically NO2 is a primary pollutant. It directly releases from car exhaust, right? And those pollutants which form when NO2 reacts with unburned hydrocarbon, or we use another term, VOCs, volatile organic compounds. What are VOCs? They are volatile organic compounds, right? So these volatile organic compounds, they also get released from car exhaust, and in these volatile organic compounds, they contain unburnt hydrocarbons, like those hydrocarbons which do not get combusted, they releases from car exhaust without being combusted. So when these unburnt hydrocarbons or VOCs, when they reach in air, they react with NO2 and they form secondary pollutants, right, which are not directly releases from car exhaust, but they form from a primary pollutant. So these volatile organic compounds, they react with nitrogen dioxide and they form secondary pollutants, and one of those major secondary pollutant is PAN. PAN, peroxyacetyl nitrate, peroxyacetyl nitrate. Right, this peroxyacetyl nitrate, it has a formula of CH3CO3NO2. They will not ask you about the structure, but let's suppose if we draw the structure, this is CH3, C double bond O, 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 N, O, right? This is the structure for the peroxyacetyl nitrate, and this is a secondary pollutant. This is a secondary pollutant because this is not directly being released from car exhaust. It is being produced from a primary pollutant. When a primary pollutant reacts with, when two primary pollutant reacts with each other in the presence of sunlight, basically this reaction will occur in the presence of sunlight. So this is a photochemical reaction. So the secondary pollutant that we get is PAN, peroxyacetyl nitrate, right? It affects lungs and eyes. The major harmful effect of this peroxyacetyl nitrate, it affects plant life, and it affects lungs and eyes, also affect plant life, right? So state the product of this reaction that contributes to state the product of this reaction that contributes to photochemical smog. So the product is pan peroxyacetyl nitrate. All right, now the next part of this question is related to equilibrium, and this time they have given us a very different type of question. Now they're saying that figure 2.2 shows how the temperature of the atmosphere varies with height from the ground. Right, on the x-axis we have temperature, on y-axis we have height, and we can see that as the height is increasing, like from 0 the temperature was around 11 or 12, whatever it is. As the height is increasing, the temperature is decreasing, right? And after a certain height the temperature starts increasing again, right? And then again it's decreasing. So as we are moving away from the sea level, as we are moving above, the temperature is varying, right? The equilibrium reaction in equation 1 has delta HR minus 168 kilojoules per mole. So this reaction 1, where is reaction 1? Yes, this is reaction 1. This one is reaction 1, equation 1. So this has a delta H where sulfur dioxide is reacting with nitrogen dioxide, right? So basically, this reaction they are talking about, SO2 reacts with NO2. This gives SO3 plus nitrogen monoxide. So this has a delta H of minus 168, right? So that means minus 168. All right. Suggest how the position of this equilibrium differs. And this is a reversible reaction. So suggest how the position of this equilibrium differs at a height of 20 kilometers compared with the height of 50 kilometers from the ground. So we have to explain the position of equilibrium, and what by position of equilibrium we just have to explain that which substance would be in a higher amount at equilibrium. So because this is an exothermic reaction, delta H for this reaction is minus 168. So that means forward reaction is exothermic and backward reaction is endothermic. So at a height of 20 kilometers, we would have a low temperature, and a low temperature means exothermic reaction would be favorable. So we can say that at 20 degrees centigrade, we would have a higher concentration of products at equilibrium. But as the temperature rises at 50 degrees, at 50 kilometers, right, at 50 kilometers, the temperature increases from minus 60 to around 5 or 10. So that means the temperature is rising. So when temperature rises, equilibrium shifts backward. As temperature rises, equilibrium shifts backward. And when equilibrium shifts backward, that means the concentration of SO3 and NO would decrease at equilibrium. Whatever it was at 20 kilometers, at a height of 20 kilometers, at a height of 50 kilometers, we would have a lesser concentration of SO3 and NO at equilibrium, right? So we can just simply write down the answer here, state how the position of the equilibrium differs at a height of 20 kilometers. So at a height of 20 kilometers, at a height of 20 kilometers, the equilibrium lies on product side, more SO3 and NO at equilibrium. But at height of 50 kilometers, temperature rises, so backward reaction occurs. As backward reaction is endothermic. It favors high temperature. Temperature rises, therefore the concentration of SO3 and NO would be less than what it was at height of 20 kilometers. Right, so whatever the concentration of SO3 and NO was at 20 kilometers at equilibrium, when the height was 50 kilometer, the concentrations will decrease, right, and equilibrium will shift on the reactants side. All right, so the next question is related to halides, group 17. The hydrogen halides HCl, HBr, and HI are all colorless gases at room temperature. The hydrogen halides can be formed by reacting the halogens with hydrogen. Describe and explain the relative reactivity of the halogens down the group when they react with hydrogen to form HCl, HBr, and HI. Right, so we have to discuss the reactivity of the halogens when they react with hydrogen. So we know this thing that hydrogen, when reacts with chlorine, it forms HCl, and it forms just simply by providing some heat or sunlight. It occurs in the presence of sunlight. And hydrogen, when reacts with bromine, this reaction requires some amount of heat. And hydrogen, when reacts with iodine, this never goes to completion. It forms a reversible reaction. So that means it is difficult to form. So we can say the reactivity of halogen decreases down the group. The reaction gets more and more difficult, right? So that means the reactivity of halogens, decreases down the group. The reactivity of halogens decreases down the group, and the reason is the atomic radius of the halogens, chlorine, bromine, iodine, their atomic radius is increasing. As we are going down, number of shells are being adding into the atom. So the atomic radius of halogens increases down the group. So that means iodine has the largest atomic radius, and as atomic radius increases, these are non-metals. Halogens are non-metals, and they form bonds by attracting the electrons of the other atom with which they are making bonds, right? So, but when the atomic radius increases, it becomes difficult. To attract the valence electron of other atoms. So that's why they get less reactive. So non-metals, they get less reactive down the group because their ability of gaining electron decreases as their atomic radii or number of shells increases. All right. So the next part of the question is HCl is a product of several different reactions. Some of these reactions are shown in figure 3.1. So this is figure 3.1. SiCl4 reacting with water, this gives HCl. NaCl reacting with concentrated H2SO4, this gives HCl. So write an equation for the reaction 1 when SiCl4 reacts with water. We know this thing that we get silicon dioxide, SiO2 plus HCl, right? And to balance this reaction, 4 moles of HCl and 2 moles of water. So this would be the balanced equation. Okay, so the next part is in reaction 2, NaCl reacts with concentrated sulfuric acid. This reaction 2, where NaCl is reacting with concentrated sulfuric acid, we get HCl. So in reaction 2, NaCl reacts with concentrated sulfuric acid to form HCl and NaHSO4, sodium hydrogen sulfate. When NaBr reacts with concentrated sulfuric acid, the products are bromine and sulfur dioxide. Right, so they are saying that when NaCl reacts with H2SO4, the products are NaHSO4 plus HCl. But when NaBr reacts with H2SO4. So we get NaHSO4 plus HBr. And this HBr is less thermally stable as compared to HCl, right? So this the H2SO4 present, H2SO4 would be in excess. This can oxidize HBr or bromide ion present in HBr, because H2SO4 is a strong enough oxidizing agent to oxidize bromide ion. It cannot oxidize Cl minus, but it can oxidize Br minus, as it is less thermally stable, a weak oxidizing agent. Br itself is a weak oxidizing agent. So H2SO4 can easily oxidize bromide into bromine and sulfur dioxide. So this is what they're telling us, that the products include bromine and sulfur dioxide. So identify the type of reaction that occurs in each case by completing table 3.1. Explain the difference in these reactions. So in reaction 1, when NaCl reacts with H2SO4, in this reaction H2SO4 is acting as an acid because it is releasing a proton. It becomes NaHSO4. One of its proton is being lost, so it is acting as an acid. So we can say that this is an acid-base reaction or a displacement reaction. You can also call it a displacement reaction. So this is an acid-base reaction, or we can call it a displacement reaction, right? But when H2SO4 reacts with bromide ion, it changes the oxidation state of bromide ion. The Br oxidation state changes from -1 to 0, right? Its oxidation state changes from, in HBr, its oxidation state is -1, in bromine, its oxidation state is 0. And H2SO4, sulfur itself, is in oxidation state of +6 in H2SO4. But in sulfur dioxide, its oxidation state changes to +4. So the reaction of NaBr with concentrated sulfuric acid, this is a redox reaction. And the explanation for this difference in reactions is that H2SO4 is a strong enough oxidizing agent to oxidize Br minus, as Br is a strong or stronger reducing agent than Cl, right? So between Br and H2SO4, a redox reaction can take place, but between HCl and H2SO4, no redox reaction will be happening. All right, now the next question is, when heated with a Bunsen burner, HCl does not decomposes, whereas HI forms H2 and I2. Explain the difference in the effect of heating on HCl and HI. So HI is less thermally stable. HI is less thermally stable. It can be easily broken down, right? It is less thermally stable due to large atomic radius of iodine, which causes an increase in bond length between hydrogen and iodine, and subsequently the bond energy decreases. It becomes easier to break the bond, right? Just remember this thing, that whenever bond length increases, bond energy decreases. So that's why HI can be decomposed, but HCl cannot be decomposed when heated in Bunsen burner due to its stronger bond energy. All right. Now, the next part of this question is, the hydrogen halide dissolve in water to form strong Bronsted-Lowry acids. Strong Bronsted-Lowry acid. The concentration of a strong acid can be determined by titration. State what is meant by a strong Bronsted-Lowry acid. So a Bronsted-Lowry acid is a proton donor. During a chemical reaction, if a substance is donating proton, that means it is Bronsted-Lowry acid. So a proton donor, and a strong Bronsted-Lowry acid means which ionizes completely. All right, now the next part of this question, this is pH titration graph, which is the new topic for AS syllabus, as previously it was in A2. This was a topic of P4, but now it comes in P2. So this is the first time it is coming in P2. And the question is on figure 3.2, sketch the pH titration curve produced when 0.1 mole per dm cube NaOH is added. So that means NaOH is the titrant, volume of NaOH. So we are adding NaOH to 25 cm cube of 0.1 mole per dm cube HBr to excess. So HBr is a strong acid. So and NaOH is a strong base. So we are adding a strong base into a strong acid, and the HBr is a monoprotic acid and NaOH is a monoacidic base. So that means both HBr and NaOH, they will react in a 1-to-1 ratio, and as their concentrations are same, we have 0.1 mole per dm cube NaOH and we have 0.1 mole per dm cube HBr. So that means to neutralize, or for the equivalence point, if we have 25 cm cube of HBr, they have told us that we have 25 cm cube of HBr. So if the concentrations are same and they are reacting in 1-to-1 ratio, that means for equivalence point will occur at 25 centimeter when we add 25 cm cube of NaOH in 25 cm cube of HBr. All right, so because we are adding NaOH in acidic solution, so the pH will start from acidic range because it is a strong acid. So let's suppose it starts from 1, right? And let's draw a straight line. So let's suppose the equivalence point will be at 25, right? So this would be at 25, and as it is a strong acid, strong base titration, so equivalence point would be at 7. So just to draw a clean graph, I have drawn these straight lines, and now we will draw the graph. So let's suppose we say that the pH, initially the pH, there would be a very small change in pH, but as we move closer to the equivalence point, pH changes sharply and we get a straight line. And as we are going into the axis, NaOH is added into axis, so that means when NaOH is in axis, we would have a pH around 13 or 14. So this would be our equivalence point. So this is the graph, the pH titration graph, when we are adding NaOH in HBr, a strong base into a strong acid. And next is we are adding 0.1 mole per dm cube ammonia is added to 25 cm cube of 0.1 mole per dm cube HBr. So this time we are adding HBr, we are adding ammonia into HBr. Again, HBr is a strong acid, but ammonia is a weak base. So we are adding a weak base into strong acid, but their molar ratio, because again ammonia is a monoacidic base, so they will react in a 1-to-1 ratio, and their concentrations are again same, 0.1 mole per dm cube, 0.1 mole per dm cube. So to neutralize, or for the equivalence point, if we have 25 cm cube of HBr, equivalence point we need 25 cm cube of aqueous ammonia, right? So again we are adding base into acid, so the pH will start from strong acid range, and the equivalence point would be again at 25 cm cube, and let's say this is 7, right? And this time, because we are adding a weak base into a stronger acid, so the graph would be something like this, right? This would be something like this. So the equivalence point, this would lie in the acidic range. This would lie in acidic range. So this would be the graph when we add ammonia into HBr, a weak base into a strong acid. All right, now the next part of this question is related to organic chemistry. HBr reacts with propene to form 2 bromoalkanes, CH3, CH2, CH2Br, and CH3 to CHBr. So when propene reacts with HBr, we get two different types of bromoalkanes. Addition reaction would occur. Complete the diagram to show the mechanism of the reaction of HBr and propene to form the major organic product. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Draw the structure of the intermediate and the major organic product. So we have to draw the structure of intermediate and major organic product. Right, so this is an electrophilic addition reaction. So first of all, let's just draw the charges on HBr. It is a polar molecule, so Br would be partial negative, H would be partial positive, right? And this pi electron density, it would attack on the hydrogen, due to which this bond will break heterolytically. Both the electrons would be taken by Br, right? And this H as a positive charge will be attached to one of the either this carbon or this carbon. But they have asked us to draw the mechanism for the major organic product, right? So if H goes to this carbon, this will gain a positive charge. And if this carbon gains a positive charge, that means it is a secondary carbocation, right? Because it is attached to directly to two carbon atoms. And if H goes to this carbon, that means this gains a positive charge, and this is a primary carbocation because it is directly attached to only one carbon. So the major product is from secondary carbocation. Just remember this thing, secondary is more stable than primary, or tertiary is more stable than secondary, but here we only have secondary or primary. So we get the major product would be that one which is forming from secondary carbocation. So that means H would be attached to this carbon, right? From where we get secondary carbocation. So this pi electron density, we have to draw the curly arrow. This pi electron density will attack this hydrogen, partial positive hydrogen, and these two electrons will be shifted to Br, right? So the structure which we get here is double bond will break, CH, H, CH, H, 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 and this is the newly attached hydrogen, and this carbon would be positively charged. We get a carbocation. This is the structure of the intermediate. All right, and this is a secondary carbocation. And we're also left with Br minus. Now, because Br has a negative charge, it would attack on this carbocation. And finally, we get our structure CH, H, all right, so now we have a Br attached to this carbon and an H attached to this carbon. So this carbon is attached directly to two methyl groups, a CH3 and a CH3 and a Br. So this is the major product, right? So explain why the two bromoalkanes are not produced in equal amounts by this reaction, because the secondary carbocation is more stable, so more chances of forming the secondary carbocation due to, why it is more stable? Due to higher positive inductive effect. And what is positive inductive effect? The electron releasing effect. These carbons, we can say this is a secondary carbocation. So these carbons which are directly attached to this methyl group and this methyl group which are directly attached to carbon, they releases some of their electron density to this carbon, this positively charged carbon. So that the positive charge intensity decreases on the carbocation and it becomes slightly stable. So due to higher positive inductive effect, which is electron releasing effect, right? So the secondary carbocation is more stable due to higher positive inductive effect. That's why they are not produced in equal amounts, right? The other one is second primary carbocation, which is less stable, less positive inductive effect. Now, the next question is the reaction of CH3, CH2, CH2Br, and NaOH is different depending on whether water or ethanol is used as a solvent. Right? Halogenoalkanes reacts with NaOH both in water and in alcoholic medium. So they're saying that both are different reactions. Complete table 3.2 to identify the organic and inorganic products of this reaction of CH3, CH2, CH2Br, and NaOH in each solvent. When 1 bromopropane reacts with NaOH in water, and when it reacts with NaOH in ethanolic medium. So when it reacts with, when CH3CH2Br reacts with NaOH in water, this is a nucleophilic substitution reaction. So the organic product would be OH will replace Br. So we get CH3, CH2, CH2OH, and the inorganic product would be this Na would be attached with Br. So we get NaBr. And when it reacts with ethanol in ethanolic medium, it would be elimination. So this carbon would lose its Br and this carbon would lose one of its hydrogen, and we get an alkene. So in case of reaction of bromopropane with NaOH, we get an alkene, propene, CH3, CH, double bond CH2, and both H and Br lost, they would form HBr. So these are the organic and inorganic products when bromoalkanes reacts with NaOH in water or in ethanolic medium. Okay, now the last question of this paper is compound J and K are found in plant oils. This is the structure of J and this is K. Now, the first part is complete table 4.1 to state what you would observe when J reacts with the reagents listed. So these are some reactions of J, and we have to write the observations when J reacts with 2,4-dinitrophenylhydrazine, which is a reagent used to test for carbonyl compound. So we have an aldehyde and a ketone both present in J. So that means we get orange precipitate when it reacts with 2,4-DNPH. With Tollens reagent, as aldehyde is present, so aldehyde will react with the Tollens reagent and we get a silver mirror formation. Both of them are redox reactions, so we get a silver mirror formation. Like Tollens reagent or Falling solution, they're used to test whether we have an aldehyde or ketone. Both Falling and Tollens reagent, they're weak oxidizing agent. They can react with aldehyde, but they cannot react with ketone. And lastly, with sodium metal. So sodium metal, it can react with the alcohol. It is slightly acidic alcohol. It can react with active metals. And when it reacts with sodium metal, releases hydrogen gas. So that means bubbling or effervescence. Right, so these are the three observations. Now J has two optical isomers. Optical isomers are basically two non-superimposable mirror images. Draw the three-dimensional structure of the two optical isomers of J. So to draw the three-dimensional structure, first let's draw all the four bonds. And its mirror image would be, we will switch the left and right bond. And now let's attach the groups. So the carbon has CHO group, CH3, and OH. So this is one optical isomer and the other would be C double bond O, CH3, CHO, OH, CH3. So these are the three-dimensional structure of the two optical isomers of J. Okay, so the next part is K is used to make the addition polymer Prespex. A synthesis of Prespex is shown in figure 4.2. Right, so Prespex is an addition polymer which is made from compound K once it converts into M, and then M is the monomer, it forms Perspex. Identify L, state the conditions required for reaction 1. So L is the reactant which is reacting with K to form M, right? And you can see the difference in K and M is in K we have this carboxylic acid, and M it is an ester link, right? So that means K is being reacted with some alcohol, and which alcohol? We have one carbon atom present here, so that means L is methanol, alcohol with one carbon atom, right? So this is methanol, and the condition, this is esterification, so the condition would be concentrated sulfuric acid plus heat. Draw one repeat unit of the addition polymer Perspex. So as Perspex is an addition polymer, so the double bonds would break, and the repeat unit for an addition polymer is very simple to draw. So we just simply draw, double bond would be broken down and we get COOCH3, CH3, and this would be the repeating unit of addition polymer Perspex. Now, use information from table 4.2 to suggest how the IR spectra of M and Perspex would differ. Now just remember this thing, that M is the monomer, M is the monomer, and Perspex is the polymer, right? So the only difference between M and L, chemically the only difference is that M is unsaturated and polymer is saturated. So explain your difference. Use information from table 4.2. In 4.2 they have given us some characteristic absorption ranges of certain bonds, and we are only interested because M and the polymer, they can be differentiated based on the carbon-carbon double bond, because M would show a peak due to carbon-carbon double bond, but polymer will not, because there are no carbon-carbon double bonds, and the carbon-carbon double bond absorption range is 1500 to 1680. So we can say that, suggest how the IR spectra of M and Perspex would differ. We can say that in M there will be an absorption. Just remember this thing, avoid writing inverted peaks or peaks, write absorptions. So will be an absorption at 1500 to 1680, which Perspex lacks, as there are no carbon-carbon double bonds. So this is how we can differ them on a IR spectra. All right, now the last part of this question is K can be made from propanone in the 3-step synthesis shown in figure 4.3. So this is K and it is made from propanone. Complete table 4.3 to identify the reagents used and the type of reaction in each step. All right, so the first we have to write the reagent for step 1. In step 1, what is happening here is that we have this carbonyl group, and in step 1 we get OH and cyanide. So that means this is the addition of, this is nucleophilic addition, right? This is nucleophilic addition, and the reagents are NaCN plus HCl, right? So cyanide ion will act as a nucleophile, it attacks on this carbon, and oxygen will gain a hydrogen, so we get this cyanohydrin. Then step 2, what is happening? Everything is same except for this cyanide converts into carboxylic acid, COOH. So this is acidic hydrolysis of cyanide. So this is the hydrolysis reacting with water in acidic medium, right? And lastly, we have a double bond present between these two carbon atoms. So that means this is the elimination of OH from this carbon and H from this carbon. So this is type of reaction is elimination. Dehydration, we can write dehydration, water molecule is lost. So this is elimination or dehydration, and the catalyst used is Al2O3. So this is the end of this paper, and I hope everything is clear. And if you have any questions, you can ask in the comment section, right? And inshallah ta'ala, I will share some more solved past papers as well. All right. Allah Hafiz.